Welcome to Mrs. Lee's Chemistry Academy, where no students are left behind. Today, we're going to talk about electrolytes and solutions. This is tied to learning objectives, LO 1.4 from College Board, that the students able to connect the number of particles, moles, mass, and volume of substances to one another both qualitatively and quantitatively. Another learning objective 2.8, that the student can draw and or interpret representations of solutions that show the interactions between the solute and the solvent. And lastly, LO 2.9, students able to create or interpret representations that link the concept of molarity with particle views of the solution. So a solution is a homogeneous mixture of solute dissolved in a solvent. One of the characteristics of a solution is electrical conductivity, the ability to conduct an electrical current. Now there are three categories of electrolytes. The first one, strong electrolytes, that they can dissolve in water completely and form ions. And these movable ions will then conduct electrical current and can be detected by a light bulb which is strongly lit. One kind is the ionic compound like sodium chloride that's soluble in water completely to form ions, sodium and chloride ions. Another one would be a strong acid such as hydrochloric acid that would dissociate completely to form hydrogen and chloride ions in aqueous solution. Another one would be the strong base such as sodium hydroxide that dissociates completely to form sodium and hydroxide ions in solution. Another electrolyte is a weak electrolyte. These electrolytes, when dissolved in water, they do not dissociate completely. They only dissociate partially, therefore forming very few ions with a lot of undissociated molecules. These few ions can still conduct electrical current, but the light bulb will only lit up dimly. For example, acetic acid and ammonia in water. Now the double arrow indicates equilibrium situation where all three species stay in the solution. You have very few ions, but a lot of undissociated molecules. The last categories are the non-electrolytes. These are the molecular compounds. Although dissolved in water, they do not come apart, they don't form movable ions, and therefore there's no electrical current. They do not conduct electricity. Here's a diagram showing the dissolving of sodium chloride, the ionic compound, in water. In water, the ions will come apart. You can see the smaller cation, the sodium ion, is surrounded by polar water molecules with the oxygen end facing the cation. The oxygen is the negative side of water molecules, while the chloride ion, the anion, being negatively charged, is surrounded by the positive end of water molecules, the hydrogen end. This kind of attraction is called ion dipole attraction. This is happening because the attraction between the ion and polar water molecule is stronger than the attraction between the sodium and chloride ions. Here I would like to show you the difference between a strong acid, like hydrochloric acid that ionizes completely, and a weak acid, such as acetic acid, that only ionizes partially. And you can see that in the diagram, the left-hand side has the hydrochloric acid completely dissociated all into ions, while the right-hand side beaker only has very few ions with a lot of acetic acid molecules stay intact. So here is a diagram showing the light bulb in terms of in a strong electrolyte. The left-hand side, the light bulb is strongly lit up. The one in the middle is immersed into a weak electrolyte where the light bulb is very dimly lit. And the one on the right is the light bulb with the electrode into a non-electrolyte molecular compound, and it is not lit up. Here's practice problem number 1. Looking at this electrical conductance diagram, where it shows that I have 1 molar sodium sulfate solution, 100 milliliter of that, and to that I'm adding 1 molar barium chloride solution. why does the electrical conductance would decrease between 0 to 100 milliliter of barium chloride added, and then it increases again beyond 100 up to 200 milliliter of barium chloride added. Now, initially, in the beaker, you have nothing but the sodium sulfate solution that ionizes completely, so I have a lot of movable ions floating around, and therefore the electrical conductivity is at the maximum. Now, as I gradually add this barium chloride to the sodium sulfate solution, the barium ion will collide with the sulfate ions to form the precipitate barium sulfate. And the solid does not conduct electricity. So now I'm reducing the concentration of ions in the solution, and therefore the electrical conductivity would decrease. At exactly 100 milliliter of barium chloride added, now all the barium and all the sulfate ions are used up to make barium sulfate precipitate, and therefore the conductivity will be at the minimum. When I have reached 100 milliliter, I continue to add more barium chloride to it. Now between 100 to 200 milliliter of barium chloride added, I have excess barium and chloride ions. Therefore, the electrical conductivity will increase again. Looking at solution, let's find a way to express the concentration. There are many other ways to express it, but here we are focused on learning molarity. Molarity is represented by the capital letter M, which means the moles of solute, either be the solid or the ions, per liter of solution. And when we dilute a solution, the moles of the particles before the dilution and the moles of the solute after the dilution are maintained the same. And knowing that mole is equal to molarity times volume, if you manipulate it from the above equation, we arrive at M1V1 is equal to M2V2. The moles of particle before dilution is equal to the moles of solute after dilution. Now here is problem number 2. How many grams of sodium hydroxide are contained in 250 milliliter of 0.4 molar solution? We take the molarity times the volume. And be sure that you convert the volume into liters, which is 0.25 liter. We obtain 0.1 mole of sodium hydroxide. And that's converted into 4 grams of sodium hydroxide. Now the next problem also deals with a similar kind of situation, but we go further in terms of how to prepare the solution. So we perform the calculations and we obtain 4 grams of sodium chromate. Now, first we mass it on balance, and then we have to find a 500 milliliter volumetric flask, the one with a round bottom and a long neck and a calibration mark. And we fill it with some distilled water first, and then we then swirl the content to make sure that sodium chromate is totally dissolved. And then we finally add distilled water to the calibration mark, and then we stopper the flask and shake it several times, and then we label it. So here's a diagram. See, we have now transferred the sodium chromate, the yellow solid, into the round bottom 500 milliliter volumetric flask. And we add water, about half fill, so that we can grab the long neck and then swirl it to dissolve the solid. And then finally, we make it up to the volume. Some students would prefer to use a little plastic pipette to add the last few drops so they don't shoot over the calibration mark. Then we stopper it, and then we shake it several times, invert it, and then label it. And it's ready for use. Now here's a diagram showing how the dilution, in that dilution problem, that the particles of solute are not changed. We start out with 10 particles in the left diagram in, let's say, 100 milliliter water. And when we add another 100 milliliter water to it to make 200 milliliter to the right-hand side diagram, there are still 10 particles of the solute. It's only the volume that's changing, but not the number of particles. Describe how you would dilute a 12 molar stock solution into 0.75 molar of hydrochloric acid into 500 milliliter. So using the formula M1V1 is equal to M2V2, we multiply volume by 12 molar is equal to 0.75 molar times 0.5 liter, and it's calculated to be 31.3 milliliters. Now here is the important part. We got to measure this 31.43 milliliter using a pipette. And we're going to use two kinds of pipettes, one being the 25 milliliter, the volumetric pipette, and the other one being the 10 milliliter graduated pipette. And it's very important that we get the right size of volumetric flask, 500 ml. We must add water to the flask first. This is a safety precaution because when you mix strong acid, concentrated acid, with water, a lot of heat will be evolved. So if we're not careful, it can result into splashing and it could harm the student's face. So we want to start out with water first, which has a great heat capacity. It can absorb a lot of heat. Always add acid to water, never water to acid. This is a safety feature. And we then fill that up with water to the calibration mark and mix it well. So here's a diagram. So assuming that in the 500 milliliter volumetric flask you already have half filled with water, then we measure the concentrated 12 molar HCl to it, and then we dilute it to the mark, and we stopper and shake and label. Practice problem number 5 has to do with concentration of ions. We have 10 grams of cobalt-3 chloride. We want to make 4.35 liters of solution. What is the molarity of the ions? So we calculate the molarity of the cobalt-3 chloride solution to be 0.0139 molar. Now to show the concentration of the ions, in 1 mole of cobalt chloride, we have 1 mole of cobalt-3 plus ion. So we multiply it by a mole ratio of 1 to 1. We still have 0.0139 molar of cobalt ions. Now regarding the chloride ions, in 1 mole of cobalt chloride, there are 3 moles of chloride ions. So we multiply it by a mole ratio of 3 to 1. We end up with 0.0417 molar of chloride ions. The last problem dealing with mixing of two solutions. We have nitric acid, 50 milliliter of 0.1 molar, and then we have another one, 100 milliliter of 0.2 molar. Let's mix it together and find the concentration of the final solution. So we calculate the moles of the first one, molarity times volume, we have 0.005 moles. Then we calculate the second one, molarity times volume, we have 0.02 moles. Adding up, we have 0.025 moles of nitric acid, the solute. And the total volume is 0.05 plus 0.1, 0.15 liter. Now the important part in calculating concentration of a mixture is that total moles divided by total volume. So now we have 0.167 molarity. Summarizing what we have learned in the lesson today. First, we learned how to differentiate between strong, weak, and non-electrolytic solutions. Then we interpret the particulate drawing to represent ionization of strong acid and weak acid. We also learned that an ionic solute is dissolved in water due to ion dipole attractions. We also examined the electrical conductance in a diagram of a precipitation reaction and explained why the electrical conductivity would decrease and then increase again. We learned about molarity using it to express concentration of a solution. We related mass to mole, to volume, to ion concentration. We also learned how to prepare a solution from solid of known molarity. And finally, we learned how to dilute a solution from a stock solution. I hope that the above lesson is helpful to you. I look forward to seeing you again next time. In the meantime, if you have any comments, please feel free to let us know. We greatly value your comments. Thank you.